20th century has seen some spectacular developments in science and technology that have really transformed our lives. All you have to do is to think about air and space travel, the personal computer and the internet, and of course, the discovery of the genetic code and the sequencing of the human genome. Well, chemists have played an enormous role in that. And one of the things we've done is we've really developed the tools to understand what makes molecules tick. Such is the pace of change in chemistry that we've gone from test tubes and colorless liquids to a discipline where chemists are working with physicists and biologists more than ever to understand how life works. In the 21st century, chemistry is moving on fast. In fact, we're moving beyond the molecule. And this new understanding is actually allowing us to design molecular systems and devices. We're going to see how this new knowledge is blurring the boundaries between traditional chemistry and the other sciences, and how a new generation of chemists is actually applying this new knowledge and answering some of the most fundamental questions of our universe. It's often assumed that chemistry, while useful, can't really answer the fundamental questions about how life actually works. That seems more like biology. But that just can't be true. Chemistry is absolutely fundamental. Take pattern formation, for example. How could chemistry actually put markings on the side of an organism? Let me show you. What I have here is the famous Belousov-Zhabotinsky reaction, which shows how chemical systems self-organize when mixed together. And what's interesting about it is that when it's left unstirred to itself, patterns magically appear within it. You just put the right molecules together and new and exciting structures appear. The problem is knowing which molecules to use. What chemists are beginning to learn are the rules that underpin these processes. And the result is that we're getting precise control over how and where reactions occur. Nanoscience sits in that gray area between individual molecules and bulk matter. Nanotechnology is one area of science which looks set to revolutionize our way of life. It's the world at the nanoscale. That's 1/1000th of a meter. Nanochemistry is an area which has been steadily developing, and now scientists are beginning to actually control organized arrays of molecules and their function.
And people realize, hey, we can design molecules now to start to do the things that we want them to do. So this is one of the typical labs where we would do some of our highly sensitive experiments.
Dr. Charles Fall is a nanochemist at the University of Bristol. He's designing molecular systems, some of which could be the next generation of medical diagnosis.
If you have the possibility to design a molecule that would, for instance, interact very specifically with a marker from a cancer cell, if you can design a material that would interact very specifically with that marker and then show a response, for instance, change color, you could put it on your tongue and take it out, and if there's a color change, then you know, okay, something is wrong, you need to see the doctor. How do you design a molecule that would interact very specifically with only one specific marker? And I think, and this is where the challenge lies.
By understanding the molecules and the interactions between them, Charles is actually designing a molecular system that can assemble itself.
If you take the example of water and oil, you shake it up, you know that it will mix into two phases. You don't have to do anything to get these things to organize in this way or to assemble in this way. They will do it by nature. We try to do exactly the same with our molecules. So we build into molecules areas, for instance, that would like water. We build areas into the molecules that like oil. So what happens is all the oily bits will assemble together, all the watery bits will get together, and this way they will self-assemble. I don't have to do anything to do that. We apply basic principles so that we can finally get to the point where we can design materials to assemble in the way that we want them.
Nanotechnology is coming to the forefront because new techniques are now available, enabling scientists to analyze substances at the molecular level. At the University of Bristol, Charles has at his disposal one of the most technically advanced buildings in the world for this research.
Fred Hale, I'm the Operational Building and Resources Manager for the Bristol Centre for Nanoscience and Quantum Information. My role is to run the day-to-day operations of the centre, providing an environment that can be used by chemists, engineers, physicists, medics. Basically, it's a bit of a research hotel, so people can come in, use the facilities here, do what they need to do. I guess I'm the hotel manager, the Basil Fawlty of the centre, really.
The Centre for Nanoscience and Quantum Information is much more than just a collection of labs. When you go below the surface, into the basement, you find something rather unique, including one of the quietest rooms in the world.
All you can really hear is your own inner noise. If you stay here too long, I find you start to swim about a bit because you lose your sense of balance because there's no real reflections.
The reason these labs are so quiet is they're specifically designed to have zero vibrations. If you're working at the nanoscale, even the vibration from a passing car is enough to move your sample.
We don't want any sort of interference, so we're concerned with electromagnetic noise, acoustic noise, and mostly with vibrations. This is a 5-ton block of concrete. You can probably see the tape moving there, so that's sunk into the floor. We've got this huge, we call ground slab, and then we further isolate the experiment on these blocks, and they work extremely well.
Shaw Fall's work in the centre involves using atomic force microscopy to look at the materials he's produced.
What you have here is basically a very sharp tip that you would pull across a surface. So if you have molecules lying flat on the surface, this tip will feel them and will lift, and basically in that way you'll be able to have a map of the morphology. So of course, for that you can imagine if you really want to look at atomic resolution of your molecules, you would need an extremely quiet environment.
This work produces some incredible images of molecules. In the future, nanochemistry could bring us a new generation of medicines.
Targeted drug release certainly has wide applications. Of course, the question is, how do you bring your drug close to the point where you want to release it? And of course, how do you shield it away from the body, and that the body doesn't see it as foreign and attack the drug before it actually gets to the point where it can actually do its work.
These are not inconsiderable problems. But with scientists around the world working on nanochemistry research, it won't be long before we start seeing new drugs and other new applications becoming available. Carbon. Its compounds are often said to be the foundations for life on Earth. But do we really know everything about it? The textbooks tell us that there are basically 3 forms: hard, crystalline diamond, soft, slippery graphite. And then there are the fullerenes, those beautiful geodesic molecules like this one. But there's more to carbon than this. Have you ever asked yourself what happens if you take a pencil and scribble on a piece of paper? That layer I've left behind is less than just graphite. It's graphene, a layer of carbon just 1 atom thick, which is set to completely change our lives. Here at the University of Exeter, they're so inspired by graphene that they've set up a centre to study it.
This is the Centre for Graphene Science.
Dr. Sharon Strawbridge is a chemist working at the centre. The centre is just one example of the kinds of collaborations between scientists from different areas, which are happening more and more as the boundaries between disciplines become increasingly blurred.
The Centre for Graphene Science was set up just over a year ago. We're looking across all aspects of graphene science. I'm obviously a chemist, I'm interested in the chemical properties. We've got engineers looking at large-scale production of graphene, and we all work with each other, which means it's very collaborative. I think that is a very, very good way of describing graphene, as a gigantic, if you like, net of carbon atoms, hexagonally bonded, or extensive chicken wire.
What's got chemists so excited is that because graphene is just a single layer of carbon atoms, this is quite literally taking science into another dimension.
We're used to a world that's 3-dimensional. It is essentially a 2-dimensional material. The physics and the chemistry involved with that is extremely interesting. But to be able to isolate a single sheet is really incredibly exciting. It's a completely new material.
The potential of graphene has opened up the door to a new generation of electronics.
Graphene can be good in electronics because it's a very good conductor, and potentially it has very high mobility, which is a measure of how the electrons in this material respond to an electric field applied along it. It can be potentially much better than silicon, which is used in technology at the moment.
We're almost down to the point that silicon will become obsolete. We've got so many transistors on a chip, and it's getting to the point now that they're so close together, you're almost at the point where they start to talk to one another and you get to problems.
You get a lot of heat generated by these transistors. And actually the limitation in the speed of computers now is not necessarily how small you can make them, but how you can dissipate that heat.
How can you get smaller? The only practical element that you could do this with is really carbon-based electronics.
IBM and MIT are creating transistors now out of graphene that can be running up to 100 gigahertz or more.
This all sounds incredible, but why aren't we all using graphene-based electronics today? One of the major problems comes when you try to isolate it. First, make sure you work in a clean room so no dust is transferred to the materials. Second, take a piece of graphite. Any graphite will do. Graphite is essentially layers of graphene stacked together. Now take some ordinary sellotape and then squish the graphite onto the sellotape until bits come off. Next, make sure it's all clean using ethanol. Then tidy up after yourself. Go back out of the clean room again. Then painstakingly search your sellotape for any one atom thick graphene that may have come off.
The thing that's holding it back is to be able to produce graphene on a large scale. At the moment, the very best quality is the graphene that we get from this exfoliation of crystalline graphene. We need to move beyond that, and that's some of the work that Monica's involved in.
In the last year there have been a lot of progress in this direction, but it's not yet possible to grow really large area of single layer graphene. The layers that have been grown, they have patches of a single layer of a few micron size, and then the next challenge is to find a way to really grow uniform graphene layers.
Despite these problems, progress is being made, and it could change our lives forever.
Maybe in 15, 20 years' time, we're moving to an era where we're going to be looking at carbon electronics. We're going to be looking at molecular electronics.
Just think how much electronics have changed in the last 10 years. Graphene-based electronics could accelerate this change to give us devices we can't even yet imagine. Chemistry is set to move us into the future, but can it shed light on our past? One of the hardest and deepest questions we can ask is, where did we come from? How did life actually start? Well, I have beside me a recreation of an experiment carried out almost 60 years ago, which was really the first attempt to try and answer this very question. It's called the Miller-Urey experiment, and it's really an attempt to recreate planet Earth several billion years ago. We have an ocean boiling away and an atmosphere containing methane, nitrogen, hydrogen, and carbon dioxide. And there is lightning in the sky.